Welcome to our AI learning series. In this video, we dive into the foundations of neural networks, starting with the Perceptron, the basic unit of all deep learning models. We break down complex ideas into simple, easy-to-understand concepts with no coding or math required. Introduction to neural networks. Neural networks are a key concept in artificial intelligence and machine learning. They are computational models designed to mimic the way the human brain processes information. Just like our brains are made up of neurons that transmit signals, neural networks are made up of units called artificial neurons or nodes, which work together to process information and make decisions. At a high level, a neural network learns by observing patterns in data. It can be used for a wide variety of tasks such as recognizing images, translating languages, recommending products, and more. Neural networks are the foundation of modern AI techniques, especially in the field of deep learning. Understanding the perceptron. The perceptron is the simplest type of artificial neural network and serves as the building block for more complex networks. It was introduced in the 1950s as one of the earliest models for machine learning. A perceptron mimics how a single neuron in the brain works. It takes several input signals, processes them, and then decides whether to fire or not, just like a biological neuron. Here's how it works conceptually. Takes inputs, the perceptron receives one or more input values. These could be numbers representing features of a dataset like height, weight, age, etc. Applies weights, each input is given a certain level of importance using values called weights. These weights can change during the learning process. Adds bias, a constant value called bias is added to help shift the decision boundary, giving the model more flexibility. Processes the data, all the weighted inputs and the bias are combined into a single value. Applies an activation function. This final value is passed through a mathematical function called an activation function, which determines the final output of the perceptron. If the output crosses a certain threshold, the perceptron produces one result, like yes, otherwise it produces another, like no. In a sense, the perceptron is learning how to make simple decisions. While the original perceptron could only solve very basic problems like linear separations, it laid the groundwork for more advanced models. Role of activation functions. An activation function is a critical part of every artificial neuron in a neural network. Without it, a neural network would simply act like a complex linear model, which limits its ability to learn complex patterns or make smart decisions. Here's what activation functions do conceptually. They determine whether a neuron should be activated or not, similar to deciding whether a biological neuron should fire. They introduce nonlinearity into the network, which allows it to learn from data that is not simply a straight line or flat surface. They help the network learn complex relationships between inputs and outputs, such as patterns, images, or sequences. There are several types of activation functions, and each has its strengths and weaknesses. Some functions mimic a step on/off, others produce outputs between 0 and 1, while others allow only positive outputs. The choice of activation function can have a significant impact on how well a neural network performs. For example, in basic models, step-like functions were used to simulate simple yes/no decisions. In modern deep learning, more flexible and smooth functions like ReLU, rectified linear unit, are often used because they are computationally efficient and help networks learn faster. In summary, neural networks are a family of algorithms designed to recognize patterns by mimicking the structure and function of the human brain. The perceptron is the most basic form of a neural network. It helps the machine make simple decisions by combining inputs, applying weights, and using an activation function. Activation functions are essential for giving neural networks the ability to handle complex, real-world problems by introducing nonlinearity and enabling learning.